Tommy tosses a ball upwards with an initial velocity of 10 meters per second. How many forces are acting on the ball 3 seconds after Tommy threw it? Okay, so as long they didn't precise it here, as long as the ball is still in flight, there is only one force, the gravitational force. What is the net force then acting on the ball? Actually, man, I just realized it here. This question is missing something. Tommy tosses, let's say, a 100-gram ball upward with an initial velocity. Now, the net force is going to be just equal to the weight. Net force is going to be equal to Fg, since Fg is unbalanced. And Fg is going to be m times g. Now, in this case, it's going to be 100 grams, that's 0.1 kilograms, times minus 10 meters per second squared. So it's going to be 1.0 newtons. Okay, we are going to finish this part with this example. It's a little long example, but broken in several questions. Laurie had to push a 400-kilogram fridge with a force of 1,000 newtons before she was able to get it moving. Yet the minute the fridge began moving, Laurie noticed that if she kept applying 1,000 Newton force, the fridge would accelerate at 1 meter per second squared. Okay? Let's understand things here. We have the mass of the fridge. The fridge didn't move. She kept on pushing and pushing and pushing, didn't move till she applied 1,000 newtons. But she realized if she keeps on applying 1,000 newtons, the fridge would accelerate at 1 meter per second squared. Now the first question, what are the forces acting on the fridge before Laurie got it to move while still pushing it? Okay, that's a good question. So this is our fridge. Okay, now Laurie is pushing. She's pushing with a force this way, let's call it FL. Since it's not accelerating in the direction of her push, there must be a force opposing her push, and that force can be only the friction force, static friction force, so F sub F. And then, of course, we have along the vertical the gravitational force, and that's going to be balanced along the vertical by the normal force exerted by the floor. The gravitational force exerted by the earth and the normal force exerted by the floor. Remember, I'm making the distinction all the time between floor and earth. That's important. Okay, now we agreed on this. The next question, what is the maximum static friction force on the fridge? Now, like what we did in the examples before, the maximum static friction force is the force that we need to apply to get it to start moving. And in this case, Laurie had to apply 1,000 newtons to get it to start moving. So my maximum static friction force is just 1,000 newtons. Okay. Now, once the fridge started moving, what are the forces acting on it? Okay. Now we'll have a graph, same kind of situation. Okay, the door. We still have Laurie. She's still pushing with 1,000 newtons. That's F Laurie, so we still have that force. The gravitational force didn't change, it's still there. the normal force still balances the gravitational force, and we know that since we know that the fridge is not going to accelerate upwards or downwards. And then there must be another friction force. The other friction force in this case is going to be sliding friction, since the fridge is going to be sliding, and that sliding friction force is going to be directed this way. What is the net force on the fridge then? Net force, remember, is the sum of all unbalanced forces. Now in this case, our forces are, let me write it, F Lorry plus Fg plus Fn plus F friction. And of course, we know that these two are balanced, so we don't have to worry about them anymore. So the unbalanced forces might be FL and F friction. But then F net, we know also that F net is equal to MA. Okay, once we know that, now what tools do we have? Which method is going to be able to get us the net force? Is it the top equation or the bottom equation? The top equation would require that we know FL, which we know 1,000 newtons, and the friction force, which we don't know. We know the maximum static friction, but we don't know the kinetic friction. If I use this alternate look at the net force, I would need to know the mass of the fridge and the acceleration. Both of these are given here, a mass of 400 kilograms and an acceleration of 1 meter per second squared. So let's go back. So a mass of 400 kilograms and an acceleration of 1 meter per second squared. So my net force is 400 times 1, so it is 400 newtons. That's my net force. Now, what force should Lorry apply then to stop the fridge from accelerating? Okay, so what force should Lorry apply to stop the fridge from accelerating? Okay, one easy way to think about it, my net force is, we just found it, 400 newtons. So Lorry is applying 400 newtons more than what we need. So if we take 400 off of the force that she's applying, we'll find out how much she needs to apply. Another way to look at it, let's find the friction force here. What Lorry needs to do is apply a force large enough just to balance the friction force. Remember, what she's trying to do here is stop it from accelerating. Stop it from accelerating. That's not stopping the fridge, just stopping it from accelerating. It's going to continue moving at constant velocity. So to do that, then let's find the friction force. In the previous question, what we had was, we said our net force is 400 newtons, and that's equal, let me write the equation first. F net is equal to FL plus F friction plus Fg plus Fn, and we said these two are balanced, so we don't have to worry about them, and we are left with 400 newtons is equal to FL, which is 1,000 newtons, plus FF. So FF is minus 600 newtons. To have no acceleration, FL has to be equal to FF, so the new FL needs to be equal to 600 newtons. question then, what if Laurie decides to let go of the fridge? What would the net force be? Okay, we saw that in the simulation. So then, if Laurie lets go of the fridge, what are the forces acting on the fridge now? Gravitational force still there, normal force still there, but then the friction still there. There is no Laurie. So again, if we apply our Newton's second law, F net is going to be equal FF plus Fg plus Fn, and again these two are balanced and we don't have to worry about them, so F net is just the friction force, and which is minus 600 newtons. What would be the acceleration of the fridge then? If I know F net, which we said is minus 600 newtons, we know that F net is equal to ma, which is 400 kilograms times a. So we solve for a. 400 kilograms times a is equal to minus 600 newtons, and a then becomes minus 6/4 of meters per second squared, okay, or 3/2, so it's minus 1.5 meter per second squared. Okay.